In statistics, we know that the population parameter is unknowable. Now, in this particular lesson on confidence interval, we will learn techniques on how we can estimate the true population mean of the population based on our sample. And this is part of our lesson in inferential statistics, wherein we're trying to judge the population based on our sample. Now, going back to my previous examples on the weight of the rabbits, let's say that this basket is my population and this basket contains all the rabbits in the world. And this illustration right here is my population, and I am interested to know the actual average weight of all the rabbits here in the basket, or basically the population. So to be able to do that, I know that the population mean is unknowable, and there's no way we can find the actual value or the exact value of the average weight of all the rabbits in my population. So what I'm going to do is to sample or to take some samples in my population to give a better judgment on the average weight of my rabbits from this population. So let's say my first sample, I took 30 rabbits, and from this 30 rabbits, I weighted them and took the average and computed for the average weight of this 30 rabbits right here. And out of these 30 samples, the average weight of this group of rabbits is 3.2 pounds. So this is my first sample. Then I take another sample of, let's say, 245 rabbits this time from my population, and I weighted those rabbits, and my average weight for this particular sample is 4.2 pounds. Now I take another sample from my population, and my third sample here gave me an average of 5.9 pounds, given that this sample size is 326 rabbits. Now, if you will notice, we are basically estimating or trying to find the estimated value of the population mean based on our sample. Now, in statistics, we will learn techniques or some techniques on how to find the range of values that will capture the true value of the population mean by using our sample. And this is how you illustrate your estimated population mean based on our sample. If you will notice, this box right here is your population mean, and we know that we cannot find, or we're not going to be able to find the exact value of this mean. However, we can at least estimate. So these two boxes right here will be our confidence interval. And this confidence interval is something that we can compute using some statistical formula. And this is what we're going to find, these two values, in our lesson today in confidence interval. Trying to estimate the population mean by the samples that we took from the populations. So that is basically the gist of confidence interval, and that's what we're going to do in computing or making inference about the population based on our sample. Now, this is a more statistical illustration on what I explained on the previous slide. So given the population mean, this time I have specifically put 80% as my confidence level. So in working with confidence interval, we have such a thing as confidence level, and that confidence level changes. And this confidence level right here is basically the width of your confidence interval that will be determined by a given problem. So in this particular example, let's say my confidence level is at 80%, and this is basically the population or the illustration of your rabbits in your population. I have my confidence interval here, which is between 3.5 and 5.5. So using a statistical technique, I already computed for the confidence interval for this particular population, which is 3.5 and 5.5. So this is my estimated population mean based on my sample. Now, once again, I did not show you the mathematical formula in finding 3.5 and 5.5. It's because I just want to make sure that you understood what confidence interval is, and that is what we're doing in this particular slide. So from the population, every time we take a sample of, let's say, 50 from this particular population, our estimated mean or our computed mean for this particular illustration will fall or will be inside this particular interval wherein the population mu is being captured by our range of values, which is 3.5 and 5.5. So on my first pick, on my first sample of 50, my mean is at 4.1 pounds, and 4.1 pounds is inside the interval. So this one has captured or is inside our values or range of values for 3.5 and 5.5. Now I took another sample size of 50 from my population, and this particular 50 rabbits right here, its average weight is 5.2 pounds, and 5.2 pounds is somewhere inside the range still. So this one right here is inside our interval for 80% or for the 80% level of confidence. Now I took another sample of 50. Now this time around, this particular sample size of 50 is now weighted 2.9 pounds. And 2.9 pounds is not inside the interval. It falls outside the range of your value, and that is possible in this particular example because our confidence level right here is just at 80%. Now if we make this wider, this particular sample right here might be captured in our range of values. But for today, we're just going to be focusing on the 80% level of confidence. Now, to write out or to summarize what we just did here in my example, with repeated sample of 50 rabbits from the population, which I just did, we are 80% confident that the true population mean will be contained between 3.5 and 5.5 pounds. So that is basically the gist of how the confidence interval works in statistics or in inferential statistics. Now to formally introduce what confidence interval is, by definition, confidence interval is an estimated range of values which likely to include the unknown population parameter. And in this case, it's the population mean. Now, the confidence interval for the population mean, when the population sigma is known, is given by this formula. And this is the formula that we're going to be working on in our lesson for confidence interval for population mean. It's going to be x bar plus or minus z star times sigma all over the square root of n, where x bar is your sample mean, your z star is your critical value, and your population standard deviation is your sigma, and your sample size will also be given in that particular problem, which is denoted by the small letter n. And this is the formula that we will use in computing the values or the range of values that we need to estimate our population mean. Now the z-star is based out of our normal distribution, and to compute for the z-star, it is given by this particular formula. We're trying to find the value of the location of our z-star, and to do that, given our confidence level, which is at C, from our previous example, my confidence level was 80%, and I'm going to use that so we can find the z-star of 80% confidence level. And this is my 80% confidence level, and to find the z-star, this particular location in your normal distribution, we will use this formula. Now z-star for 80% will give us 1 minus c, which is 0.80 divided by 2, which gives us 10%. So this particular 10% is basically the area in your tail region. So this two tails right here measures 10% of your total area in this particular normal curve. So this 10% is the area, but we're not concerned about the area, we're concerned about this location. And to find the value of z-star, or this particular location, you can use your z-table or your calculator to find that value. And in your calculator, you just need to use inverse normal, 0.10, and it will give you the actual location of that particular z-score, which is at 1.28. So this is how you find the z-star, which you will need in your formula for the confidence interval later on. And here are some common confidence interval and inferential statistics that we will use. We have the 90% confidence level, 95%, and 99%, and their corresponding Z star. So for 90%, it's 1.645, for 95%, it's 1.960, and for 99%, it will be 2.576. Now, before we can actually compute for the confidence interval, it is very important that you understand why we're looking for these two values right here in our confidence interval. And that's what we're going to be working on in our next examples.